Hi everyone, welcome to the Z module, and the Z module is about the conservation laws and the elementary particle physics paper. So many conservation laws are there. The specific conservation law that holds the elementary particle is the conservation of hypercharge. Hypercharge represents the sum of the baryon number B and the strangeness S. So we all know that the baryon number is always conserved. So hopefully the Y, which is the hypercharge, the quantum number will also be conserved in the strong interactions. But whereas it is not conserved in weak interactions. So there is a formula to relate the charge with isospin, baryon number and the strangeness. So that is nothing but Q is equal to T3 plus 1 by 2 Y. T3 plus 1 by 2 B plus 1 by 2 S. And this relation is called as the Gell-Mann-Nishijima relation. What is Gell-Mann-Nishijima relation? The relation that relates the charge, isospin and the hypercharge of the elementary particles. In case of the strange mesons, baryon number is 0. So in that case, Q will be equal to T3 plus 1 by 2 S. For non-strange mesons, S is equal to 0. So the Q reduces to T3 plus 1 by 2 S. So strangeness is a conserved quantity in a reaction such as two protons combine together to produce a proton with lambda elementary particle and the kaon. By substituting the strangeness number, we'll be able to identify the strangeness of the unknown elementary particle called kaon, which will be equal to plus or minus 1. So, the strangeness number for pi meson is 0 for pi plus and pi naught and eta naught mesons. Since the baryon number B is 0, the strangeness S is equal to the hypercharge. So, the strangeness is an independent new quantity, but it could be combined with Q, T3 and B in various possible ways. So, here there are the possible ways. First case, when S is equal to 0, there are three possibilities out there. First case, when b is equal to 0, t is equal to 0. When b is equal to 0, t is equal to 1. b is equal to 1, t is equal to half. So these are the three possibilities that could be done with the formula that is Gell-Mann-Nishijima relation. So by substituting these values, we'll be able to find out the values for Q from which we can identify the elementary particle. If Q is 0, then it should be a neutral meson. If Q is plus 1, it should be a pi plus meson. If Q is 0, then it is pi naught meson. If Q is minus 1, it is a pi minus meson. Similarly, by substituting B is equal to 1 and T is equal to half, and by calculating the value of Q, the nucleons are identified. Right. Similarly, in the same way, S is equal to 1 and S is equal to minus 1 possibilities are ruled out, from which the values of Q are used to identify the elementary particle, and S is equal to minus 2, minus 3 are also used here. In case of hadrons, the strangeness must be conserved, that is delta S is equal to 0 for fast reactions. So there are few decays such as sigma naught decays to proton plus pi minus elementary particle, or psi naught elementary particle decays into lambda naught and pi naught, which results in the delta S is equal to 1. So from this we'll be able to find out the relation between delta S and spin. So delta S is equal to 2 times delta 3, from which delta T3 is equal to 1 by 2. T3 is nothing but the isospin. So you can also consider a reaction where two protons are involved that results in the pair of pi mesons. So we'll be able to verify the conservation of charge, baryon number, isospin, hypercharge and the stress and the strangeness. So next property is charge conjugation. What is the charge conjugation? This operation that changes the sign of the charge of the particle without affecting any of the properties that is related to charge. So only the sign alone has been changed. So we can also define this charge conjugation operator by transformation between a particle and the antiparticle. So it is found experimentally that the operation of both strong and electromagnetic interactions is invariant to charge conjugation. So the strong and electromagnetic interactions will not vary under the charge conjugation conservation laws. So it is not concerned in the weak interaction. For example, a weak interaction does not distinguish between the original system and its charge conjugate system. So here there are few examples where we can make use of the charge conjugation operator called C. So C Q C inverse if it results in minus Q. So this is what the exact way in which the charge conjugation conservation is used. Similarly, with respect to the hypercharge, with respect to the baryon number, and with respect to the lepton number, and with respect to the muon number. So there are few elementary particles called gamma, pi naught and eta naught mesons and the positronium atom which are transformed into themselves by the charge conjugation. So whenever the charge conjugation is applied to these elementary particles, there may not be any change. They themselves will be the final product because they are the neutral elementary particles, because they are their own antiparticles. Or I can say that these are the self-conjugate or the true neutral particles. The neutron B is equal to 1, Y is equal to 1 and K naught mesons are not invariant under C. A system is said to possess charge conjugation symmetry or to be invariant under charge conjugation, then it is impossible to know that it has undergone charge conjugation. So here, according to Dirac's theory, the charge conjugate that corresponds to the wave functions of the positrons is given by C is equal to e power I alpha I phi I alpha y. What is phi? Phi is in any arbitrary function. If the phase is 0, then phi is equal to 0. In that case, the value of C will be reduced to I times alpha y. So if in case of the single photon, the operator C acting on the gamma function will result in the minus gamma. So for a system of n photons, we need to multiply by n gamma. C of n gamma is equal to minus 1 the whole power 1 whole power n gamma. If there is n photon state is an eigenstate of C with an eigenvalue of minus 1 the whole power 1, then C operator which is acting on pi naught will result in only pi naught because the antiparticle is the same. Similarly, if pi plus meson and pi minus mesons are not the eigenstates of C, then it results with a minus sign. So the next property is with the space inversion invariance. This parity principle says that there is a symmetry between the original image and the mirror image. If there is a symmetry, then that conservation law is called as space inversion invariance. Or to put it in a nutshell, reflection of every point in the space through the origin of the image is impossible to obtain in nature, then the system is said to violate the law of parity conservation. For example, the human body is a good example for mirror symmetry. And other examples are the body of the car is symmetric except for the symmetry, but it is not the case as it is possible to design the car with the steering wheel on the other side. So the quantities may can have either odd parity or the even parity. Ordinary scalars such as temperature, electric charge, energy have the even parity. The ordinary vectors such as momentum, force, electric field have the odd parity. Pseudo vectors such as angular momentum, magnetic field behave as vectors under rotations but have the even parity. Similarly, pseudo vectors have the odd parity. All phenomena involving strong and electromagnetic interactions alone do conserve parity. In these cases, the system can be classified by the eigenvalue of the parity operator called P. If the parity operator acts on the wave function psi of x, that results in the e power I alpha psi. What is e power I alpha? E power I alpha is called as an eigenvalue. So the parity operator acting on the psi of x will be resulting in psi of minus x. P squared of psi of x will be equal to psi of x, where the eigenvalues of P are plus 1 or minus 1. So the parity of the photon depends upon the mode of transition and it is due to the change of the electromagnetic current J under the parity operation. So here there are few hyperons which do have got the positive intrinsic parity and K meson, eta naught meson have the negative parity. Pions have the negative parity as they involve in the strong interactions with the nucleons. The conservation of parity requires the Hamiltonian of the free system which commute with the parity operator. Hence pH minus HP should be equal to 0 and it can also contain the pseudo scalar operator which is represented by I dot P. And the weak decay of the K mesons, which was difficult to reconcile with the parity conservation, is known as tau theta puzzle, which is explained by Li and Yang. So this suggested that the weak interaction was not invariant to space reflection. And the combined inversions are also possible. In case of combined inversions, PC and CP can be combined together to undergo this conservation process. So with this, we'll close here and we'll continue the remaining conservation laws in the next video.